Hi everybody, I'm Sahand, I'm from TUM. I finished my master thesis on the topic that I'm presenting a couple of months ago, and so I'm going to talk about deep reinforcement learning, deep inverse reinforcement learning, which I'm going to explain for autonomous driving. Reinforcement learning is an area of machine learning which deals with agents interacting in an environment. Basically, the point is, for the agent, we want to see what is the best action to take at every possible state in order to maximize the future expected reward. A recent example that you all heard about in the news is the AlphaGo from DeepMind, which tries to maximize the reward, basically tries to win. So the reward is pretty simple there. The thing is, when we want to train these kind of agents, we need a simulator. The simulator first has to simulate the dynamics of the game or the environment, like AlphaGo. But another important thing is the reward function. In games, it's pretty simple to say what is the reward function. But in some applications, for example, in driving scenario, it's pretty hard to define the reward of driving well. So, if you want to think about how do I define the reward function to make my agent act optimal to it in order to drive perfectly, it's pretty hard to define. Therefore, inverse reinforcement learning is the area which deals with finding the correct reward, or not correct, but approximate reward function for the reinforcement learning. What usually you do is you look at the expert. You look at the demonstrations of the expert and you say, okay, what is this expert optimizing in order to have this near optimal behavior? And this is a classic way to solve the inverse reinforcement learning problem. So you guess an initial reward function, and then you apply the forward reinforcement learning. You learn an agent that makes some demonstrations, and then you compare the demonstrations of the agent with the expert, and then you try to make them closer and closer to each other. You can see the details later at my poster. I'm not going to go into the details. The problem is the state space. When it becomes large, it's pretty hard to compute the value function in reinforcement learning. That's actually what DeepMind solved in DQNs and also in AlphaGo, using the neural networks. And we also used this and took advantage of these DQNs in order to solve the inverse reinforcement learning problem. I don't know if this video, I noticed I didn't convert it correctly. There's a very nice video, I will show it to you later, that shows how we learn to drive without knowing any reward function and just by looking at the expert. And in the end, what we got is kind of a reward function that it's hard to compare because evaluation is not easy. We don't have the true reward function. We just try to interpret that. I don't know if there's time for me to interpret it for you. Otherwise, I do it at the poster. I just try now. For example, you can see the sensors that show the distance of the car from different obstacles, the walls or anything that comes in front. I'll just give one of the sensors. For example, this sensor, there's also a black one that you can see here. As you can see, the reward function, if we are at a distance of 1 from the wall, let's say the distance of 1, is high, but it immediately drops when we go to distance of 2, because we realize that we don't want to drive on the lanes and we want to drive between the lanes. Thank you.